Good morning students. Welcome to our online video class of chemistry. In previous section we had discussed about photoelectric effect. I hope you have understood what is photoelectric effect. Today we will discuss about atomic spectra.
Dual nature of electromagnetic radiations. We had studied about photoelectric effect and black body radiation. And this phenomena could explain the particle nature of electromagnetic radiation. On other hand, radiations exhibits a phenomena of interference and diffraction which indicated that they possess wave nature. So it may concluded that electromagnetic radiation possesses dual nature, particle nature and wave nature. Next topic is evidence for the quantized electronic energy level, atomic spectra. What is a spectrum? Let us understand first what is a spectrum. The speed of light depends upon the nature of medium through which it passes. As a result, the beam of light is deviated or refracted from its original path as it passes from one medium to another. And it is observed that when a ray of white light is passed through a prism, the wave with a shorter wavelength bends more than one with a longer wavelength. Since ordinary white light consists of waves with all the wavelengths in the visible range, a ray of white light is spread out into a series of colored bands called spectrum. The splitting up of white light into series of color bands when white light is passed through a prism is known as VIBGYOR. Sunlight is composed of a collection of electromagnetic waves having different wavelengths. The prism bends the light of different wavelengths to different extents. In your lower class, you also have learned that the phenomena of splitting up of light into 7 colors is known as dispersion. From this, we can say what is called spectrum. What is spectrum? When a ray of white light is passed through a prism, we get a series of colored bands called spectrum. As we study that when a ray of white light is passed through prism, the wavelength with a shorter wavelength bends or deviates more than one with a longer wavelength. Therefore, the light of red color, which has longest wavelength, is deviated the least, while the violet light, which has shorter wavelength, is deviated the most. The spectrum of white light that we can see ranges from violet at 7.50 into 10 to the power of 14 Hz to red at 4 into 10 to the power of 14 Hz. Such a spectrum is called continuous spectrum. It is continuous because violet merges into blue, blue merges into green and so on. A similar spectrum is produced when rainbow forms in the sky. This visible spectrum is only a small portion of electromagnetic spectrum. When electromagnetic radiation interacts with matter, atoms and molecules may absorb energy and reach to high energy state. High energy state is unstable state. It is less stable. And to return into the normal energy state, that is lower energy state and is more stable. It emits radiation in various regions of electromagnetic spectrum. Atoms gives discontinuous or line spectra. The spectrum of atom are not continuous. The spectrum given by atoms consists of a series of bright lines or bands. A band is a group of spectral lines and is separated from each other by a dark space. Each line in spectrum corresponds to a specific wavelength. There are two types of atomic spectra: atomic emission spectra and atomic absorption spectra. Atomic emission spectra. When a sample of atomic vapor is heated to a high temperature, the atoms in the vapor get energized and excited. That is, atoms present in the vapor, when we give high temperature, get excited by the absorption of energy. These energized atoms then returns to their stable ground state by emitting electromagnetic radiation of certain definite wavelength or frequencies. These emitter radiations produce a series of bright light separated from each other by dark space. We have studied that at the higher energy stage, it is less stable. Then, in order to attain the stability, it returns back to the lower energy stage by the emission of radiation. Then, these emitter radiation produce a series of bright lights separated from each other by dark space. This is shown in this picture. The spectrum of radiation emitted by a substance that has absorbed energy or a series of bright lights separated from each other by dark space produced by excited atom is called atomic emission spectrum. And each line in the emission spectrum corresponds to specific wavelength. Therefore, each element gives a unique pattern of lines in the spectrum. No two elements give the same pattern of line in their spectra. For example, the emission spectra of hydrogen, helium and mercury is shown in this figure. When you observe this picture, you can understand each element gives its own characteristic pattern of lines in the spectrum. In 1859, Robert Bunsen and G. Kirchhoff developed a spectroscope for studying emission spectra. A spectroscope consists of a prism for dispersing the light and a telescope for observe the spectra. The spectroscope in which telescope is replaced by a photograph film is called a spectrograph. The photograph of the spectrum is called a spectrogram. The picture A and B are illustration of a simple prism spectroscope, that is A, and the principle of spectroscope for obtaining emission spectra, that is B. Atomic absorption spectra. When a sample of atomic vapors is placed in path of white light from an arc lamp. If we place a sample of atomic vapors in a path of white light which is formed from an arc lamp, It absorbs the light of certain characteristic wavelength and the light of other wavelength get transmitted. This produces a series of dark lines on a white background. These are the dark lines. These are white backgrounds. A spectrum containing lines of definite wavelength is called discontinuous spectrum or line spectrum. The line spectrum is also known as atomic spectrum. And the usefulness of atomic spectra are each element gives a characteristic atomic spectra. No two elements give same pattern of lines in their atomic spectra, since all elements give a definite pattern of lines at certain definite frequencies or wavelength. Hence, the atomic spectra can be used in chemical analysis to identify and estimate the elements present in any sample. The elements rubidium and cesium were discovered this way. Next, we are going to discuss about atomic spectrum of hydrogen. The hydrogen spectrum is an important piece of evidence to show the condensed electronic structure of an atom. Hydrogen atom has only one electron. The atomic spectrum of hydrogen is the simplest pattern of the spectral lines. Hydrogen spectrum has played an important role in the development of atomic structure. The emission spectrum of hydrogen atom is obtained by passing electric discharge through hydrogen gas at low pressure. Hydrogen gas contains large number of molecules. When an electric discharge is passed through hydrogen, the molecules of hydrogen breaks into atoms. The electrons in different hydrogen atom absorb different amount of energies and are excited to different energy states. Excited atom tends to return back to the stable ground state by emitting light. Different excited electrons adopt different routes to return to various lower energy levels or the ground state. As a result, they emit different amount of energies and thus produce a large number of lines in the atomic spectrum of hydrogen. An experimental setup for the emission spectrum of hydrogen atom is shown in this figure. This is discharge tube containing hydrogen gas at a low pressure. When an electric discharge is passed through hydrogen, the molecules of hydrogen breaks into atoms. This hydrogen atom then absorb energy from the electric spark and get energized. This energized state of atom is called what? Excited state. When the population of the atoms in the excited state increases, it returns back to the lower energy stable ground state by the emission of radiation. The hydrogen atom emits bluish light. When the ray of this bluish light passes through the prism, a discontinuous line spectra consists of several sharp lines is obtained. Such a spectrum is called line spectrum of hydrogen. The hydrogen spectrum consists of several series of lines appearing in the different regions of electromagnetic spectrum. The 5 series are Lyman series, which occur in the UV region, ultraviolet region of electromagnetic spectrum, and the Balmer series of lines which occur in visible region. The Paschen series, Brackett series and Pfeffer series which occur in ER region, infrared region. In 1884, Johann Balmer examined the emission line spectrum in the visible region. and it was found that it has 4 prominent lines designated H alpha, H beta, H gamma and H delta in the red, blue, green, violet regions respectively. After the observation, Balmer analyzed the result and showed that if the spectral line of hydrogen spectrum are expressed in terms of inverse of wavelength, that is lambda inverse or nu bar, the visible line of the hydrogen atom spectrum obey the formula 1 by lambda equals nu bar Cm inverse equals 109677 into 1 by 2 square minus 1 by n square, where n is an integer equal to or greater than 3. That is n equal 3, 4, 5, etc. Soon after, 4 other spectral series for hydrogen were discovered. To account for the presence of other spectral lines, the Balmer equation was modified. The equation now used for describing the hydrogen spectrum is called Rydberg equation. The Rydberg equation is nu bar equals 1 by lambda, which is equal RH into 1 by n1 square minus 1 by n2 square, where RH is called Rydberg constant and the value of RH is 109,678 centimeter inverse, and n1 and n2 are integers where n2 is greater than n1. For Lyman series, n1 equals 1 and n2 equal 2, 3, 4, 5, 6, 7, etc. The electronic transition is from high energy levels such as 2, 3, 4, 5, 6, 7 to lower energy n equal 1 level. And the line lies in ultraviolet or UV region. And for Balmer series, n1 equals 2 and n2 equals 3, 4, 5, 6, 7. And the electronic transition is from high energy level n equals 7, 6, 5, 4, 3 to n equal 2 level. And the line lies in visible region. And for Paskin series, n1 equals 3 and n2 equals 4, 5, 6, 7. And the electronic transition is from high energy level to lower third energy level n equal 3. And for bracket series, n1 equal 4 and n2 equals 5, 6, 7. Electronic transition is from n equal 7, 6, 5 to n equal 4 level. And the line lies in infrared or IR region. And for P fund series, n1 equal 5 and n2 equal 6, 7. The electronic transition is from n equal 7, 6 high energy level to lower n equal 5 level.